We'll finish up this section on Ka by doing a problem with percent ionization that also introduces the concept of how sometimes it's not appropriate to ignore the X, the change in original concentration of an acid. So this one says calculate the percentage of hydrofluoric acid molecules that are ionized, and they give you a 0.1 and then a 0.01 molar solution. And I will also take a look at the impact of concentration on percent ionization. So now we're in the fallback mode. You write the equation, and of course somewhere you write the expression. This time we've omitted the water, and the values given are that you have a 0.1 molar concentration of hydrofluoric acid. We let X represent the change in concentration, and so we have an increase in X of the hydrogen and fluoride ions and a decrease by X value in the molarity of the hydrofluoric acid. So if you solve this equation by ignoring the X, and if you go up and look at the top of the problem, you go to Appendix D and you get 6.8 times 10 to the minus 4 is the Ka, you can quickly solve that X, the final concentration of hydrogen ion, is equal to 8.2 times 10 to the minus 3. Now the problem with that, and unfortunately they don't show the work here, is that if you took 8.2 times 10 to the minus 3 and divided it by the original value of 0.1 molar, you'd find out that that value is greater than 5% of the original concentration. We call that the 5% rule. And you have to be careful when the Kas get to be relatively large of ignoring that X. However, the good news is, at least from what I heard, that the AP exam is no longer going to have quadratic equation type problems. But I want to show this to you anyways. This time, at the top, what you would see is an expression that shows the X not being ignored. And we've rearranged the equation for X squared equals the original concentration minus X times that Ka. And that number, 10 to the negative 4, is your hint that that's a fairly large Ka, and therefore the X should not be ignored. So we do some math to rearrange that expression and get it into the form of the quadratic equation. So now's the part where inside your calculator, hopefully you have the quadratic equation programmed in, because you would have your A, your B, and your C values that you'll enter into the expression, and you end up, of course, with a quadratic equation with two possible answers. When you get your two possible answers, you're going to find out that one of them is a negative number, and of course that doesn't make sense, so the only one that would work for a positive value for a chemical concentration or percent ionization will be the positive value. So you can find out then that X would be equal to 7.9 times 10 to the minus 3. That would represent the hydrogen and fluoride ions that formed when hydrofluoric acid ionized. Take that concentration, either one, over the original, times it by 100, and you'll see that it has 7.9% ionization. And so for a weak acid, that's relatively strong. We use hydrofluoric acid to etch glass. Bonded to that crazy fluorine ion, it of course is sort of a scary thing, so we don't keep any hydrofluoric acid in the lab. Now notice what happens if you do the same thing with a 0.01 molar solution as in part B. Again, you're not allowed to ignore the X, so the person substitutes in the Ka, 6.8 times 10 to the minus 4. We have an X squared representing the hydrogen times fluoride ion concentration, and then the original concentration is 0.01 minus X. You would, not shown here, have it eventually come out in the form of a quadratic equation. Using the quadratic program in your calculator, you would find that X, the concentration of hydrogen, is much larger, 2.3 times 10 to the negative 3. And when you turn that into a percent ionization, and of course, that would be the part 0.0023, or 2.3 times 10 to the minus 3, divided by the whole, the original 0.01, now we get a 23% ionization. And I think what's important about this problem is not necessarily that you know how to do the quadratic equation, but that you recognize that making the concentration more dilute for a weak acid drove the equilibrium of that original expression to the right. You got more things to ionize. And a way to think of that is that when you diluted it out by a factor of 10, it's like the left-hand side goes, oh, we don't have enough ions over there on the right-hand side. Let's hurry up and go ionize with the water and form more ions. So dilution of a weak acid's concentration is going to shift its equilibrium to the direction of producing the larger number of particles, which of course in this case would be to the right-hand side. Now, there is another type of problem which you might encounter about polyprotic acids. And if you notice here, you can see that all of these acids have more than one hydrogen that can ionize. And therefore, it's possible that they can have more than one Ka. The difference between Ka1, 2, or 3, if they had 3 hydrogen ions, is just a numerical representation of the ability to lose the first, the second, and if they have a third one, the third hydrogen ion. So you can see that the Kas can be relatively largest on the Ka1, but by the time you get to the Ka2s and the Ka3s, they get pretty small. So for most purposes, if the subsequent Ka values are 1,000 times or more smaller than the original Ka1, then you don't really have to worry about them too much. So let's do a particular problem. Sometimes you do, but let's do one where you don't have to worry about that. When you go to get your water out of the jug in our classroom, a lot of times if you measured the pH of it, you'd find it slightly acidic. And that's because it sits there with the CO2 in the air that's reacting with it to form carbonic acid. So they're telling you that the solubility of CO2 is 0.0037 molar. Doesn't dissolve very much, but some. If you're at 0.1 atmosphere pressure, apparently, interesting choice of pressure measurement, and at standard temperature. So when it reacts with the water, it forms carbonic acid. So sometimes you're given a reaction that looks like this, but you have to turn it into a Ka reaction by switching it over and showing how much of that hydrogen carbonate or carbonic acid would exist in the form of ions. So all we have is an initial concentration, and your first reaction would be show the hydrogen carbonate breaking apart or ionizing, and this would be its first ionization. Here it is losing only one hydrogen ion, leaving behind a hydrogen carbonate ion as the conjugate base. We have an initial concentration. We can go to a chart and find its Ka, which is not too large, not too big, so that's good. We get to ignore the x because it's something times 10 to the minus 7. The change would be plus x for the hydrogen carbonate and the hydrogen, and we get to ignore the change in x because the Ka is so small. Substituting in the values and ignoring the x, you will get this expression down here. Notice that in the first problem, part of the problem right here, they were, cursor, there you go, they were using to get this particular answer. They went ahead and used the quadratic expression. That's not necessary. We're going to not use the x, solve for x, and we find that the concentration of the hydrogen ion is 4.0 times 10 to the minus 5. Once you have that final concentration, always go back and check what the problem wants. They want pH. So you'll take a negative log of 4 times 10 to the minus 5, and you would find then that your pH of that carbonic acid solution is not very acidic. It's 4.4, relatively speaking, to a strong acid. What if the problem wanted to know what is the concentration of the carbonate ion? This time you get to assume that it goes through another loss of a hydrogen ion. This time we start with the hydrogen carbonate, left as the conjugate base from the previous reaction, and show it losing a hydrogen ion and forming a carbonate ion. The starting concentration is what we ended with from the previous problem, 4 times 10 to the minus 5 for both of those. We don't know what the carbonate ion concentration is. All we know is that it'll increase by some value. This time we'll call it Y to distinguish it from X. Now, of course, the Ka2 is so tiny, we're automatically going to ignore any minus Y that you might see or plus Y that you might see over here. So I've got my equation, I wrote an expression, I substituted my values, and you can see it's pretty simple because the hydrogen carbonate and hydrogen ion concentration are equal to each other. That is equal to 1 when they're divided by each other, and that the concentration of the carbonate ion at the end of the second ionization is 5.6 times 10 to the minus 11. Notice that that's very, very small, and also notice that the carbonate ion concentration is the same as the value for Ka2. So only a tiny amount of that HCO3 will turn into hydrogen ion and hydrogen carbonate ion. Okay, so that's our sample exercise for a polyprotic solution. Let's stop here and we'll pick up with weak bases and Kb in the next vodcast.